you can easily show that we're talking a few orders of magnitude compared to digital technologies, and that all those orders of magnitude have been realized. Those aren't just theoretical orders of magnitude.
Think for a minute about all the information that makes you, the DNA in your body. Now imagine hundreds, thousands of times more information in even tinier molecules, compressed in a much smaller space than your body. Dr. Brenda Rubenstein has been thinking about this for years, and her work is pushing the boundaries of what's possible in data storage. In this Season 1 bonus episode of Bringing Chemistry to Life, we speak with another member of Chemical and Engineering News's 2019 Talented 12 about their work and trends in their field. I'm your host, Paolo Braiuca, Senior Manager of Global Market Development at Thermo Fisher Scientific. We began by asking Dr. Rubenstein about how her career in theoretical chemistry began and how it's evolved.
I decided to go into theory because I always love mathematics and some of the rigor of mathematics, not just the rigor in terms of how let's say difficult it might be, but also the way it makes you really think about and assess whether you're right or wrong. When you can put a number on something, you can ask yourself, am I getting the mechanism right? Am I understanding something deeply? And so I was always interested in trying to understand things from that end. So I always liked the mathematics, but I also always really liked the science. I'm someone, as you're suggesting in your intro, who really actually likes experiment. I like thinking about the dirty details. Dirty details of biology, dirty details of physics, dirty details of chemistry. And so over the years, I sort of realized that my niche was in the middle. I don't like things to be completely dirty, but I also like the rigor. And so theoretical chemistry seemed to be a very nice mix of the two, where you can actually probe things that you couldn't just solve on a chalkboard, but at the same time, you could also say, do I truly understand what's going on here?
It's very interesting. And if I try to oversimplify your research interest, I can see how you seem to be working on a couple of fairly different areas, right? On one hand, you have more traditional, proper theoretical chemistry type of work, more even methodological, if you wish, particularly with your stochastic electronic structure theory, research in the Monte Carlo, etc. But or maybe even your biomolecule simulations. On the other hand, you have what probably you yourself define alternative computing, which is fascinating and unusual, right? The combination of these two and the alternative computing concept in particular, I would say. So why does this look so different than any other theories that I know or have ever met before?
Well, I hope that's not true of every theorist, but it's because of exactly what you're saying. So I really enjoy experiment, and I do enjoy seeing things happen in the lab. And so I'm very excited to work on problems that can bring me closer to experimentalists. I'm known to have a lot of collaborators just because I like that thought process. I like talking with people who know completely different things than me and seeing where we actually overlap. And so I do really like going into those dirty details and trying to understand them. And so even though the works look very, very different, a lot of the work that I do, particularly the biophysics work and the alternative computing work, is really trying to say, can we use theory to do better experiments? And can we use theory to understand the experiments that we're doing and redesign them in a better way? So in the case of the biophysics work, I'm super interested in trying to predict how proteins evolve. And I got into this before it was cool. Now I think we understand why it's important to figure out how things like viruses evolve and their proteins evolve. I got into that because I really wanted to understand this problem and understand how can we drug things in, let's say, a pan-viral way, or how could we drug things against evolution? And that's a hard problem, but computation and theory can offer an answer and accelerate that process. So I was interested in that regard. The same also goes with computing. So a lot of the different computing architectures that people are thinking about, and these kinds of architectures are kind of on the edge computing. That's the way people tend to think about them. These computing architectures, not quite clear what they should look like or how best they should be constructed at this point. So I'm talking about quantum computing and biological computing and chemical computing. And so you really do need theorists or computational people to be able to say, this is where we have to go experimentally to realize these things. So I really like that combination of using theory to drive and help experiment. And that's why you see a few different areas that maybe don't look like the traditional, what the traditional theorists would do.
So we'll try to get into both aspects, right? More the theory and the relationship between the theory and the real world, if you wish. But I like really to start from your alternate computing, just because I find it fascinating. And I've read a couple of your papers, and I'm totally out of my comfort zone here, but I found the idea really one of the most out-of-the-box concept that I've encountered in recent years. It's really creative, all right? So in a nutshell, if I understand correctly, what you're trying to do is experimenting with the use of chemical molecules for data storage and computing, rather than using traditional semiconductor technology. It's, I believe, because you can potentially overcome some physical limitations of current technologies. But I'm always fascinated, and I like to start from there, by the idea generation. So why even getting into this, and how did you start?
That's a great question, Paolo. So, I had ideas about this, a long time ago, and I really, actually, even as a graduate student, I remember I was at Los Alamos for a summer working on theory, like you would call it, and I was thinking about, what kind of things molecules can do for you, can you control their behavior, and so forth. But what really galvanized this later on was, so DARPA put out a call, and they were interested in can we store information in more compact ways than we currently do. And so, I read that call, and then I started realizing very quickly, why couldn't we just store information in molecules? And if we're going to store information in molecules, it's going to be incredibly dense. Why can't we store that information in even more compact molecules than let's say, biomolecules? So people have over the years stored information in DNA. Of course, our bodies do it all the time, and people have engineered DNA to do so. But I thought about it and said, we can be even more dense if we were able to use even smaller species. And so that kind of got this started. And I have to give a lot of credit, during some of those initial thoughts about being able to store information in molecules and being able to compute. I talk with collaborators at Brown, so we have a lot of, Brown's a fun place because we have people that are willing to do crazy things and, kind of swim out of their lane sometimes. We had some meetings with a few people who were just interested in this. They didn't really know why they were there. They just knew that they were interested. They didn't have any, particular ideas. But, we started, drawing things out. I brought in a spectroscopist. I said, hey, we're probably going to have to be able to interrogate these molecules at some point. And he said, okay, I don't know what you're talking about, but I'll give it a go. And we brought in some engineers who were just very good at exactly the quantitative things that I'm talking about, really breaking down an idea and saying, can we do this? Can we do that? What can we do? And when we all got together, after I provided some initial fodder for saying maybe we can store information in molecules, we came up with the concept that we could probably store information in mixtures of molecules. And so what you can say is that a bit, the presence of a bit could be mapped onto the presence of a molecule in the solution, and the absence, the zero, could be mapped onto the absence of a molecule in solution. And if you have a big solution, then you have a whole bunch of bits. And so after that initial idea, a lot of us started working and thinking about how we could really make that happen. And this is an excellent team story. I mean, they really took my crazy theorist idea of how this could work, and they made it into real tools. So the spectroscopist I talked about came in and said, this is how we'd be able to interrogate millions of molecules. And then the engineers came in, and then they said, this is the exact, these are exactly the combinatorics, and these would be the errors that we'd be seeing and reading things out. And it was really an amazing brew of people. And so then since then, we've been working on computing. And that's also been driven by some crazy theoretical ideas I had about how molecules could machine learn. And then again, the engineers on the team sort of helped us make that all happen. And so it's been a lot of fun in that regard, and that's how we got to where we are today.
So the idea really was exploring the potential of information data storage density. And this is really because if you compare a normal transistor is like 5 nanometers or something like that, and while
Sure.
a molecule can be a couple of order of magnitudes or even more, smaller, right, potentially.
Yep.
So if you could store molecules
exactly.
with the same kind of density that you store transistors, you could
Yep.
immediately jump up the information density by, hundreds of times potentially.
Exactly. And so you can easily show that we're talking a few orders of magnitude compared to digital technologies, and that all those orders of magnitude have been realized. Those aren't just theoretical orders of magnitude.
Okay, can you now try and describe how that works? It's going to be a challenge because you can't use any slide, but I'm sure you can do it.
Mm-hmm. So in terms of the storage, the way this works is that what we can do is whenever we store digital information, we map, let's say, a text string, or we map an image to ones and zeros. Once you do that mapping, which is, everybody does this all the time whenever we do information processing, then what we can do is store each of those ones and zeros in the presence or absence of a molecule in solution. So let's say we have 1,000 molecules, and they're all distinct molecules. So we can clearly detect which one's which using some means. We've used mass spectrometry to do that just because of the throughput that we can get, but you can use other means. So as long as you can distinguish those molecules, what you can then do is say molecule A will represent the first bit. And if molecule A is in a solution, then molecule A will represent that bit. You'll have a 1. If the molecule is not in a solution, then you'd have a 0. And you can do that for all of the molecules, and then all of a sudden you've stored a lot of information. So that's the basic concept, just using presence or absence of molecules. But we can get much higher storage capacity if we really think about mapping whole large strings to smaller subsets of molecules. So we can do things like sparse encoding and lots of fancy engineering things to increase our capacity overall. But it's that basic presence or absence that's really the foundation for our storage technique.
So if I understand correctly, the idea of using a presence or absence of a given molecule, which is predetermined as being, a specific member of a position in your bit sequence, right? Is that you can actually avoid having the sort of ordered repetitive sequence you have in biomolecules like DNA, and you can actually do some storage in what in my mind is a disordered solution of a number of different
100%.
molecules.
You're absolutely right, Paolo. So we're trading that order for disorder. By doing this in a disordered solution, we are gaining density. So we are in fact able to store more densely than DNA can typically. We're also able to get rid of some synthesis barriers in the sense that sometimes in DNA, if you want to make extremely long, tailored strings of bits and encode them in your sequences, that can require very special synthetic procedures to do that sort of high throughput and regularly. So we get around those issues. Of course, we trade that, as usual, we trade that for other issues. So in terms of computing, the issue there is if you're dealing with things that are disordered, you have to be a little bit more clever about how you're actually doing that computing. So if you just have a DNA strand, a sequence, you can do exactly what Turing told us to do. If you have a disordered sequence, it's a little bit harder to do things. But those are some of the exciting things that we're thinking about now.
Indeed. And I believe that the number of beats will depend on the sensitivity of your analytical method. So how many molecules can you really put in your mixture while being able to discriminate them and recognize them in your whatever analysis you run?
Yeah, at the moment we can do tens of megabytes, which actually, once we do all of our encoding and some of the tricks I was alluding to earlier, that turns out to be something like 10,000 molecules. And that's actually not so easy in the sense that you start filling your mass spectrum, like the whole thing starts getting filled up with peaks. What we realized that the key thing there is actually we used machine learning to help us dig through the mess that we get. And without that, we wouldn't have been able to do this. But, we are reaching that 10,000 number, which is reasonably impressive.
So what do you do? Do you run analysis of the single in molecules, then random mixes of them, and you build up complex regression methods? So to be able then to learn how to recognize them in a complex mixture? Is that the way it works?
Absolutely, exactly. So we build a training set, and then we learn which are the the peaks that really identify a specific molecule. So there's not just one peak, but there are a series of peaks that will correspond to that molecule. And once we know that, we know some subset of peaks that will best represent it, then we use those peaks to detect the molecule in future mixtures.
I'm just curious about the chemistry, because I guess you need to pick molecules that mix well together, they don't react when you put them together, and that are easy to make, reproducible, that you don't need to purify too much. You're dealing with a big library here, aren't you?
Yeah, so you're hitting on day one when we wanted to do this, the headache that we had. We thought we're just going to end up with these glassy solutions that we're not going to be able to probe because nothing is soluble. We haven't seen that. We actually haven't seen that in the systems that we've been using. So the molecules that we've been using are what we call UGI molecules. So they're multi-component molecules. They're made by multi-component UGI reactions. The reason why we chose those molecules is because of the fact that they have combinatorial scaling. So if you have different pieces and you're putting those pieces together, there are lots of different combinations of ways that you can put those pieces together. So that creates lots of molecules. It turns out for all of the UGI mixtures that we've done so far, we haven't had the issue that that it was too insoluble that we couldn't actually do some detection on it. So we haven't seen that yet, but I think you're definitely getting at a deeper issue, that if you really did push the information density, the volumetric density, as far as you possibly could, we probably would hit some of those issues at some point, but we haven't seen that yet.
And I guess, am I correct if I think that you don't really care whether your yield is always good, because in any ways you train your analytical system, right? So it doesn't matter if you have a 75% conversion and 3 byproduct, or if you've got a highly pure UGI reaction product there, because as long as your machine learning is able to recognize what it is, that's all that matters, isn't it?
That's absolutely right. So it turns out we do get very high yields. I remember, again, when we were first starting on this project, I was talking to a synthetic chemist in our department who does these kinds of reactions. And I said to him, as a theorist, obviously you're not going to get perfect yield all the time. And he said, no, you're going to get a 99% yield. And we did. And in the small volumes that we've been using, we use nanoliter volumes. We've absolutely seen that. And so our yield has been very high, but we also have that backstop, like you're saying, is that if we train, we'll be able to detect whether the product is there or whether the product is not there. And we can do that.
It's interesting. Obviously, this is a proof of concept, because you still need a big mass spectrometer and a very sensitive one at that. So it's not something that I can really see as close to being able to replace my computer on my desk, but I think you have actually proven that it can be used, and in a way it can probably be brought forward in some way. So what is the future of this?
Yeah, so we're starting to work on that feature right now. So you hit on one of the key issues is the size of the mass spec. And this is an interesting scientific issue where we're working on miniaturized mass specs here at Brown. It just so happens that we have that capability here at Brown. There are a couple of people who work on that kind of technology. And so we're trying to bring down the size of the mass spec. There are a few approaches that we're working on right now. If we can bring down the size of the mass spec, that helps a lot. What we also need is a lot of liquid handling. So we're thinking about how do you use microfluidics to make what you want and also to make it efficiently. But once you get those two components down, so you're miniaturizing the synthesis and then you're miniaturizing the detection, you're basically almost there. So you would be able to in fact encode what you want to store, get the microfluidics to make it, and then be able to detect it when you want to read it out. So that would be like a miniaturized molecular hard drive. And so that's very foreseeable. I think the harder question then is what computing do you do on top of that? And again, that's something that I, as a theorist, I'm working on very hard right now.
What about the stability chemically?
It's somewhat hard to know in the sense that what we did was when we started this experiment, we set aside some of these molecules and just saw if they degraded or not. So far, they have not. And I think it's been something like 2.5 years. So they haven't degraded in that time. That's a good sign. I guess the theoretical way we're thinking about this is how stable are our molecules. The oogies are very stable in general. And the other comparison against DNA is obviously DNA has a lot of enzymes that attacks it. These molecules really don't. You'd have to actually come up with some natural catalyst that catalyzes these oogie reactions and breaks them apart. And there is no such thing. These are, I think, even hard to break apart industrially or synthetically. And so as a result, we want to say that we're probably more stable than DNA, although time will certainly tell.
We hope you're enjoying this episode of Bringing Chemistry to Life. Stay tuned at the end of the episode for information on how to access content recommendations from our guests, as well as information on how to register for a free Bringing Chemistry to Life t-shirt. And now, back to our conversation. Your work seems to be focused on finding this right compromise between the theoretical rigor and the computational demand. So again, you seem to be very pragmatic in your approach, and there's a lot of creativity in that, at least from my perspective. So can you speak a little bit about this part of your work and what it is about, what are your objectives, and why it is important to you?
Yeah, so the other mainstay of much of my research is trying to create what we call new stochastic methods, which exactly like you're saying, what they try to do is they try to solve very complex problems, complex electronic structure problems. Those problems involve trying to figure out how molecules behave and materials behave. We try to solve those problems using random numbers, which increases the speed at which you can solve them, while also not compromising the accuracy with which we can solve them. And pragmatic for me is trying to find a way to get to the properties that we want to know so that we can actually design materials. So a lot of my work is focused on trying to make methods so that we can figure out material phase diagrams, figure out material behaviors before we ever have to go in the lab. And there's a lot of theoretical work that has to go on under the hood. Some of that work is yes, day-to-day work where you're really trying to figure out better ways to improve a number. But also a lot of that work, once we get to apply the fruits of our theoretical labor, is work in taking those methods and actually learning from them, applying them to a material that we never understood before. So, for example, one project in my group right now is taking some of those methods and really trying to understand what's happening in monolayers of 2D materials, some magnetic 2D materials and some alloy 2D materials, so that we can design better 2D materials. And it turns out for these monolayers, you can't get an answer experimentally for some of their properties. Some things you can understand for multi-layer systems, but not monolayers. And so it's exciting to take the theory and actually see it in those applications, so that you're understanding that's something that's entirely new.
What is a motivation for this line of research? Is it looking at a real experimental problem and trying to apply theoretical chemistry and modelization to solve it? Or is it more on the methodological part of it and then trying to find some real example on where to apply and validate the model?
So I think the best problems are a combination of both. So maybe this comes back to your earlier comments. What kind of theorist am I? But I'm someone who really likes to design methods with a key application in mind. And so we do a lot of methods development so that we can then get to these applications that, for example, fill in gaps in our knowledge, or just allow us to do things that we never could do before. So I try to build the theory for those purposes. And at least for me, sometimes I personally find if you're just doing theory so you get a slightly better number and you never hold it against experiment or never try to get experimental insights, a lot of times that boils down to looking at decimal places, and you can kind of get off track in my opinion, in the sense that you're creating better and better theoretical tools, but but is that actually making a societal impact? So I try to at least keep the societal impact in mind. I think it's an important thing. I think we can't sort of work in this box that, yes, I think basic science is important, but at the same time, I think we have to at least be thinking about how are we spending our time and how are we making the world a better place. And so I try to chain all of my method development to some application that I think is important at some point.
You mentioned the applications of your work on kind of material science problems, but obviously you work also on biomolecules. You cited at the beginning, and if I look at biomolecules being much more complex systems, this is where quantum mechanical methods have only recently gained some real ground because of the stronger available computational power. But all in all, we can still say that molecular mechanics and force field approaches are still playing a major role there. So here, conceptually, it's a completely different game, right? There's no rigor. It's actually a super simplification of a problem, trying to reproduce experimental results, really. So it's a more of a sophisticated regression of experimental evidences to some sort of simplified mathematical model. So what is, obviously you're looking at it from a different perspective again, and what is your take on this complexity of the mathematical engine behind the model and its correlation to the experimental reality for big systems like biomolecules?
Yeah, my question is always, maybe again it's pragmatic, is what do you need to describe the science that you're doing? And so in many cases for biomolecules, if you're not thinking about catalysis, you don't need the quantum mechanics. It doesn't matter quite as much. And so that's certainly true with a lot of the evolution experiments that we do when we're not thinking about active sites. So if we're not thinking about active sites, then we can certainly get away with a highly classical description, and that description can be quite profitable for trying to obtain different insights. And so I sort of view it as what level of rigor do you truly need? I don't want to get 20 decimal places just because I can. I want to say how quickly can we solve your problem and also do it in an accurate fashion. So the same kind of ideas that I use in stochastic electronic structure are the same kind of ideas that I also use for biophysics, where we have a huge amount of sequencing data that's coming through. There are a lot of high throughput experiments that are being continually developed for the past 10 years or so in the biophysics community. How can we keep up with those experiments while providing accuracy? Your question is also interesting because it brings up a part of my work, which is also trying to use machine learning to accelerate these methods. So there, instead of trying to fit that huge experiment like you're talking about, or many experiments, we're actually kind of bootstrapping. We're taking more expensive methods, and then we're taking the information, the key information that we glean from those more expensive methods, and then feeding them into less expensive methods to accelerate our methods overall. So I think your question is very very important given what's going on right now, because we're at the point where we can actually bridge all of those different levels of theory using things like machine learning in ways that we haven't been able to before. And so maybe these dichotomies are not going to be as strong as they once were.
And speaking about machine learning, what's your take on the recent results from the DeepMind's AlphaFold, for instance? That seems to be a good example to bring here.
I'm really excited about those results. Of course, I always have a certain skepticism with respect to machine learning. Its ability to extrapolate, our ability to interpret what's actually going on. But I'm extremely excited for them in the sense that, I'm happy if we're able to bypass a certain amount of very computationally burdensome theory, even though that's part of what I do. I'm happy to see that, because it's actually going to further those societal aims that I was talking about earlier. So I'm very excited to see that work. I'm excited to see how far it goes. That's sort of the key question for me. What kind of accuracy can you truly get from these things, and is it enough for most experiments? And I'm also very excited about the prospect of machine learning actually being able to help us find scientific problems, what is the scientific problem that needs to be solved, and also potentially to help us develop theories. If we have a huge amount of data and we really can't put equations down for it, well, then maybe machine learning will lead us in the right direction. So I think all of this is exciting. It complements the work that we've been doing on the physics side for quite some time, and really accelerates the kinds of ideas that we've had, but haven't been able, the problems that we haven't been able to solve.
Anyway, I just want to move from the science a little bit more about your involvement in the education inequality and everything you do to promote STEM and access to science and education for low-income students. I mean, that's a very interesting aspect of your personal and professional experience that I'd like to discuss.
That's been an undercurrent throughout my life. So I grew up in a working class neighborhood in New York. It's the kind of neighborhood, my teachers when I was younger, they said, we can tell that you're not stupid, but at the same time, you'll never have the money to go to an Ivy League school, and you'll never have the ability to get the tutors that you need to get there. I did end up getting there, but at the same time, people from that community, these communities will never have access to that kind of education, overwhelmingly so. And certainly in the United States, those are most of the communities that we have in the United States. I mean, if I go here, I teach at Brown now, which is an elite institution. I can really start counting on my hand the number of high schools that send people to institutions like Brown. It's pretty rare that you see different ones. And so there's a huge issue with equity and access. And I spent my life really working on these issues. A lot of the things that I'm working on right now are things having to do with serving the Rhode Island community that I live in. So Rhode Island of the northeastern states is essentially the poorest northeastern state. Our educational system is in shambles, and this has been reported in the New York Times. It's no secret. Providence schools don't do well, and so I've been working very hard to provide students in our area with research experiences. And some may say, well, do they have the background and do they have the ability? The best high school researcher I've ever had in my lab was someone who was getting C's in math in a town that was exactly like the one I grew up with as a kid, a very working class town. You don't get a great education. He came in here, he just had the perseverance and the ability to program and debug like crazy. There are much better off students who just couldn't sit down and try to figure out why something's going wrong, and he would do it no problem. And so I've tried to provide opportunities for them. I direct the Rhode Island Project Seed program, which offers research internships to roughly 10 high school students every year. And I also work on the Rhode Island Advocate program, where we try to work with students to create science projects. And most of them have never had science projects. They've maybe even not really had science classes. In Rhode Island, science education is really spotty. And so I believe in trying to give people who don't have these opportunities new pathways in life, so that they can at least understand what science is and maybe go into it later on. And actually, most of them have. Many of them said, hey, I never thought I would do computer science. And then they did, and they're doing very well at it. So I'm very happy to do those kinds of things.
And we perhaps need a few more people like yourself, and maybe getting everyone else, know what you're doing can inspire someone else, and maybe the revolution can start from the bottom. And again, congratulations for what you're doing for that. That's very, very admirable. There's a final question I always ask as we come to the end of our chat. Brenda, you are extremely bright, with a great future ahead of you. You're still very young, but you have accomplished a lot, and you have an important, even social role you're playing. So what is one piece of advice you'd pass on to a young student or a young scientist just starting in their careers now?
So think big, and try to seize every opportunity. Life is short, as we're seeing now throughout the pandemic. You never know when you're going to get an opportunity. So do your best to put yourself in the position to seize opportunities and really to make the best of those opportunities.
That was Dr. Brenda Rubenstein, Assistant Professor of Chemistry at Brown University and one of the Chemical and Engineering News' Talented 12. Thanks for joining us for this Season 1 bonus episode of Bringing Chemistry to Life. And keep an ear out for more If you enjoyed this conversation, you're sure to enjoy Dr. Rubenstein's book, video, podcast, and other content recommendations. Look in the episode notes on our webpage or in the app you're using to listen to this podcast for a URL where you can access these recommendations and to register for a free Bringing Chemistry to Life t-shirt. This episode was produced by Matt Ferris, Matthew Stock, and Emma Jean Weinstein.